Thanks everyone for joining today's Space Syntax Lab seminar. This is our final session of the term, and there is no better way to conclude that than to hear from two scholars who have played a central role in the development of space syntax, Dr. Nick Dalton and Professor Ruth Conroy Dalton. Today, they will speak about second-generation visibility graph analysis, area-weighted overlap for better movement prediction. Earlier developments of this work were presented at the Space Syntax Symposium in Nicosia, Cyprus, and have since been published in a journal article, and I will share the links to these materials later in the chat. Nick is an associate professor of computing at Northumbria University, and his research has significantly advanced the field of space syntax. He contributed to the development of early analytical tools, including Axman, and played a key role in methodological shifts from actual analysis to angular and segment-based analysis. His work integrates computational methods with architectural theory, enabling more precise modeling of urban movement and spatial networks. He works at the intersection of architecture and computing, developing algorithms and software that bridge disciplinary boundaries and extend the analytical capabilities of space syntax research. Ruth is a professor of architecture at Northumbria University. She has previously taught at the Architectural Association, the Georgia Institute of Technology, here at UCL, and Lancaster University. Her research focuses on the relationship between the spatial design of buildings and environments and their influence on how people understand and interact within those spaces. She's a leading expert in space syntax analysis, spatial cognition, pedestrian movement and wayfinding, and she's deeply committed to centering the user in architectural design. Now, before I hand over, as usual, if you have any questions during the talk, please put them in the chat so we can address them at the very end of the session. And with this, I would like to hand over to you, Nick and Ruth. The floor is yours.
Okay, thank you very much. I'm the one in front of the presentation, so I'm going to be doing most of the talking up front. Let's just start off. So, as mentioned, this is based on a paper. Oh, it needs a link. This is based on a paper called Beyond Binary Connections. And this is now linked to another paper, which is the Visual Experience and Spatial Configuration, Weighted Isovists in Barnsbury Street Network. And hopefully we'll get a chance to look at OmniVista 25 when we're finished, but let's see how things go. Let's go back to the beginning. And the beginning of everything, well, not the beginning of everything, but there are many representations of space in space syntax. The most significant one from our point of view is the idea of Benedict's isovists. Benedict wasn't the first person to come up with this, but he was the most kind of well cited in the area because he kind of created this idea of area perimeter ratio and inclusivity. And obviously, Benedict, I think, recently died, so it's a kind of quite a loss to sort of space syntax kind. And what makes isovists quite interesting is their relationship to an emotional and experiential appreciation of space. So it talks to some quite complex relationships that we have with space. And Ruth and I have been doing work over the years. So you've also got kind of ideas like drift and so on. And again, Sam McElhinney has been doing some great work in the more kind of recent time about kind of isovists as objects. But for those of you that are unfamiliar with isovists, just to kind of do a quick recap, basically, if you have an urban or any space whatsoever defined by these kind of occlusive walls, so kind of walls, we can pick a point in space, call it P, and then we can find the area of everything we can see from P in elevation. And again, if you look at this one, it's a bit like if you have a laser pointer and you track the laser pointer around, that line, that polygon, is the boundary of the isovist. Now, isovists are very key to VGA analysis. So, in 2000 or 1999, Turner and Penn produced this kind of making isovist syntactic. And what they introduced at this point was the idea that if 2 points in space, if a second point in space is inside the isovist of the first one, then there is a potential there. There's an intervisibility link between those 2 points. And again, there are multiple ways of doing this, but the most common of which is, do both isovists exist within each other's boundaries, basically? And if that's true, then both isovists can see each other. There are other ways of doing these interconnections. So, for example, if an isovist is inside another isovist's kind of point, then there is another kind of intervisibility there. But we're going to stick to the normal ones. But then what happens at this stage, and VGA was a big step forward, because what you do is you start off with these isovist points and you build up a graph, a network. And from this network, we can then apply syntactical measures to it, like integration, for example. And that ends up providing kind of diagrams a bit like this, where integrated points are red in the kind of color spectrum. And again, this kind of strongly correlates with movement. And VGA analysis is one of the kind of pillars now of understanding how of our research, the broader fields research. The question that Ruth and I brought to this was that we take all this rich data of these rich information of these isovists, and then we kind of reduce it down to a very simplistic notion of, do these 2 isovists see each other? So it's reducing all this large, complicated, interesting information and reducing it down to its very bare essentials of, is there a connection between these 2 points? And the work here began with the question saying, well, what happens if we have a more sophisticated way of measuring all that? So, yeah, we seem to be throwing away a lot of information. So again, you know, if you look at the work of Franz and Wiener, they were looking at kind of exploring isovist-based correlates between spatial experience. And there is this kind of broader notion of revelation, which is, if you're moving from a small space to a big space, you're gaining a lot of information. But then if you're moving from, so if you're doing this one from A to B, there's a lot of gain of information. But here, you're kind of narrowing things down. And again, classic space syntax, classic VGA doesn't really represent that. So the initial kind of question becomes, what happens when all connections are not equal? But what does it mean by this? Now, we could use a lot of different metrics, like we could be talking about moving from a large round space to a small space, or moving from a spiky space to a round space. And one of the other questions this gives us is, do connections have to be symmetrical? With a Boolean network, can I see you, can you see me? Connections have to be, are always inherently symmetrical. And this is a big question we're asking today. But as Ruth pointed out in a paper about following your nose, when we go from A to B, we might use one path, but when we go from B to A, we might use another. So again, this is some nuance in our understanding of space, which isn't kind of well represented by the pure binary connections of traditional VGA. So we began by looking at isovist intervisity overlap. So what does that mean? That means if we say start off with a space, let's call it A, and we look and we move to space B, we see that we've not really moved out of the room, and we've not really discovered much new information. So A is that green one there, and B is that reddish, that blue one there. So if we move from A to B, so that's everything you can see from A, and that's everything that you can see from B. And we just moved a bit in the room. We don't really have a lot of new information available in this kind of overlap space. But let's say we're moving from A to, and if we do a union of those, an intersection of those 2 spaces, we again see that most of A and B are encapsulated in this union space. But if we're moving from C to C, that's the new information. If we're moving from A to C, we're getting a lot of new information available to us. So again, just looking at something simplistic as area, moving from A to C has a lot of new information, and there's a lot less area of overlap. So the intersection is quite small. So just looking at these as geometric elements for a section, we can talk about the kind of Boolean algebra of shapes. So we can take A and do the intersection of A and B, and that leaves us this intersection, which is everything that's in A is in B. We can also do the union between A and B. So if we join these two spaces together, we can end up with a kind of unified single space that's everything that's in both. We can also subtract one from space from the other. So we can subtract A from B, and that leaves us that space there, which then is very similar to the intersection. And then we can subtract B from A, and again, that leaves us everything else. And finally, we can do exclusion, which is everything in the union which is not in the intersection. So these are all the spaces that are not common between these two spaces. So let's just stick with intersection. Again, for this paper, it's a very simplistic way of working. So to understand the kind of inherentness of it, what we want is a measure where if A and B, so you can see A here and B is this large overlapping space, if there's a large distance there, we need a number that's close to 0, and that represents very little information change. And if we go from A to B, and there's very little overlap, we want that to be closer to 1. So how do we deal with the fact that these areas of overlaps are quite big, and yet the areas involved are different sizes? So moving from here to here is quite significant, but from here to here is even more significant because of the relative sizes of the objects. And the way we can handle that is we take the intersection area and then we divide it by the area of either the area we're leaving or the area we're entering. Again, there's an asymmetry there. So we can end up with a measurement S, which is the amount of area here divided by the area of X. And we can easily observe that that measurement of X to Y is different from the measurement from Y to X because we're looking at different areas of overlap. So that's interesting. That creates an interesting overlap measure. So in beyond binary connections, we established that there's an improvement with observed correlation between asymmetric area of overlaps and observed movements. We also used stochastic isovist placement, and that was just a kind of time-saving device because we wanted to process things relatively quickly because it was experimental. So this leaves a number of questions. The first question is, was the improvement in correlation with observed movement, and I'll come back to that in a moment, was that due to the fact that we had asymmetrical areas, or was it due to the fact that we were dealing with area of overlap? And finally, was the improvement just some function of the fact that we were using stochastic isovist placement and maybe stochastic isovist measurement was favoring the measure? Would this still work with traditional gridded-based VGA? So, two important questions and one sort of slightly, teasing question. So the solution was to develop a symmetric area of overlap and try again also using traditional VGA grids. So that's what we did. So the symmetrical measurement basically says, let's divide the area of the intersection by the union of the areas. So now it doesn't matter which way I'm going. If I'm going from X to Y or Y to X, I'm still going to end up with the same measurement. It's still going to be based on the area of overlap, but it's not going to be based on which, it's going to be symmetrical and not based on symmetry. And again, to do this, we need to subtract both numbers from 1. So we get a value of 0, which is a value close to 0 if there's a great deal of overlap and a value from 1 if we have a very little overlap. And again, we're looking at ratios here, so it doesn't really matter what units we're working in. We have no units. We're just working in arbitrary kind of arbitrary unitary spaces. Let's go. So we end up with 2 equations, one of which is the asymmetrical version. And again, the function A here is what is the area of overlap between this polygon and that polygon. And what's the we have the symmetrical value U. So this ends up with a complex weighted graph in both cases. We end up with 2 graphs that have exactly the same networks. In fact, we end up with 3 graphs with exactly the same networks. And in all 3 cases, we end up with 3 different sets of weights. So we can see in this traditional case, which is if I'm at a point alpha and I move to point gamma, in traditional VGA, I'm still seeing that. So there's no change. There's only a change of depth of 1. Whereas with weighted VGA, we end up with quite a sophisticated or quite a nuanced kind of moving from here to here is no little change, but moving from here to here is quite a big change. So let's just kind of establish kind of terminology now. We've got traditional topological VGA, which I'm going to be calling classic VGA. We've got the area of intersection divided by the area of union, which I'm calling the symmetrical VGA, and the area of intersection divided by the area of destination, which I'm calling the asymmetrical VGA. So the asymmetrical one is the one that we presented in the bounding papers, and the classic one we've done previously. But what's new in this presentation is the impact of symmetrical. So let's think about this for a second. If it is all due to area of overlap, we'd expect that the symmetrical values and the asymmetrical values would be very similar. If it's all due to the asymmetry, we'd expect that the symmetrical value will be closer to the classical values, and the asymmetrical values would have a much bigger value of difference. Okay, so let's have a look at what's actually happening. And by the way, this time we've done everything with traditional VGA grids. So here is looking at connectivity. So here we've got traditional VGA, and we can see that these values change. So if you look at area 2, that's quite a change there. So that's the asymmetrical, that's the comparison between VGA and asymmetrical VGA. If you notice, these areas are bluer. That area is bluer. So these are making these areas more segregated. Let's look at the comparison to symmetrical. So if we look here, we see that, again, we get some interesting points, like this point here becomes very intensive, but we're not seeing much differences in the bigger distances. There are some, but not more. So if we're looking at just straight connectivity, then that's pretty interesting. We're getting some differences between that and that, but interesting differences between this and that as well. So what we can now do is do a case study, just like we did before with the observations of Barnsbury, movement in Barnsbury. So this is Barnsbury, for those that are not familiar. It's an area of London. You've got King's Cross, St Pancras down here. It's mostly residential with kind of a shopping street up here. These values were taken from gate counts. The map was slightly different. And again, I'm not really worried that the observations that this area has changed slightly, because we're comparing like with like. We're comparing the observational data here. The map's the same. So we've got the same VGA map, the same isovist map here. And we have the same observations, and we generate the same graphs. So we generate the graph like this. So this is a VGA style gridded version, and this is a visualization of the log of total depth. Now, obviously, we don't have relativization for the other 2 systems, so it makes it fair to remove relativization for the VGA as well. And we can see here that Caledonian Road is the kind of most integrated streets, but actually a lot of these streets are actually quite integrated as well. So a lot of strong movement across the kind of world. And we get the usual kind of mixing of colors from one to the other, as we'd expect. Again, if we look at symmetric VGA, what it's done is it's kind of slightly emphasized this second axis here, which is interesting. And if we look at asymmetrical, we'll see that actually there's quite a big drop here. It's really strongly promoted the distance down the major pedestrian street. So that's how the numbers look. But what we can actually do is go out and compare the observations. So what we've done here is the observation counts have been done by gate counts. And what we've done is we've taken the closest isovist. And again, this isn't a VGA isovist. This is just from the previous paper. Here we have a point, the closest isovist to that gate we've picked. We take the integration value for that measure for those gates. So we're going to have three measures. We're going to have VGA depth from total integration, total depth from that point for the classic space syntax, the asymmetrical version and the symmetrical version. So if we do traditional VGA, we kind of get what we'd expect, an R squared of 0.447. Again, if we started to relativize, we'd expect to improve in observations. And again, we don't typically use VGA at the kind of urban level. So, but again, we're making a strict apples to apples comparison here. If we look at symmetrical VGA, we see that we get a rise of R squared to 0.571. So we've gone from 0.53 to 0.17. So that's gone down a bit. And if we go to VGA, it goes up to 0.53. Actually, is that the right numbers? Let's have a look. So these are, that was for one particular case. And we can see that generally the R squared, okay, so the other R squared was the wrong R squared. This is what happens when you make slides when you're tired. So you can see generally the R squareds for VGA are 0.47, 0.4 something. The symmetrical R squareds are 0.5-ish, 0.3, 0.5. And the asymmetrical ones are, again, higher still. So generally, what's happening is the asymmetry is still causing an improvement, and the area of overlap, so the bulk of the improvement seems to be from the use of area of overlap, but we're still getting a small improvement in terms of asymmetry, applications of asymmetry. So you can see all of these ones are just slightly better, and these ones are better still. So what's interesting now is that what we've actually got is a double boost. So area of overlap has boosted the correlation with observed movement, and then asymmetry has boosted that again. And that's the kind of big take-home message I want to kind of leave you with. Now we're kind of getting close to the end. So the conclusions here are the effects are not just due to the use. So the effects are not due to the use of stochastic placement, because again, what we're using here is we're getting traditional VGA. It's not due to the size, because again, we've tried this with different sizes and we're still getting a relatively improvement. The asymmetrical area of overlap appears to outperform both the symmetrical and traditional VGA. And so the big kind of take-home message now is it's this asymmetry that appears to be fruitful in terms of pushing forwards further investigation. So the area of overlap has definitely improved correlation with observed movement, but the asymmetry looks promising for where we should be kind of thinking about next. So limitations, I've used total depth because, again, there's no equivalent for radius inside the systems we've just created. This is an identical like-for-like comparisons. The graphs were the same. If it's connected in the traditional VGA, it's connected in the weighted VGA. It's just that there's a number. They are identical points, identical isovists. And it should be it should be confessed that area of overlap is more expensive to compute than just Boolean connections. But we're working on algorithmic improvements that would help us kind of with that. So future work, I hope to be looking at radius measures and how to apply radius. I'm hoping to look at choice because, again, I think choice will produce new and more interesting measures. we've only looked at area of overlap so far. Now, it could be that there are other measures of the isovist. And again, there are lots of very rich isovist measures that Benedict and others have produced. And again, we're looking to unpick what is it about the asymmetry that improves the overlap over the strength. And of course, the important thing here is to start talking about looking inside buildings rather than looking at the relatively easy observations outside buildings. Buildings are much more complicated and nuanced devices. So again, the urban environment was picked because it makes a simple like-for-like comparison. The software now is available on GitHub if you want to download it, and it processes SVG outlines. With that, I'm going to obviously promote our paper that's forthcoming in IJAR and open up for questions.